Hello, everyone. Thank you for coming here. We have Dr. Zintao Yan today, who's going to present about autonomous vehicles and the safety behind it. I'll hand it over to Dr. Chen.
That's brave, Betsy. I thought you were going to share more. Molina, would you like to share more?
I could say generically. So we have a group on campus called the AI in Society group. It started around 2017 or so to talk about at that time AI was still rising. I guess it continues to rise, but it was still early days. We about 3 or so years ago we started this seminar series. The group has people from all across campus. The initial group includes, besides me, it has faculty members from civil engineering, from humanities and social sciences, in particular, a couple of philosophers, and also a person from library science. So it's a mixed group. But in the meantime, now we have maybe 50-ish people, faculty members, and we cover like every domain of expertise on campus, including like veterinary medicine and textiles and everything else, where AI is influential. So today we have a speaker from Michigan, but Dr. Dangje Chen, who's from the civil engineering department, is going to give an introduction, the proper introduction of Shintao. And in the meanwhile, Mansi, just to make sure, are we being recorded? I don't get a notification.
We are being recorded, yeah.
Okay, all right. Thanks. So I will go on mute.
Okay, thank you, Messi and Molinda, for the introduction. So it's my honor to introduce Dr. Xintao Yan for the webinar today. So I'm going to make it brief and then leave it to Xintao to share the exciting piece. So Dr. Xintao Yan is currently affiliated with the University of Michigan. So he received the bachelor degree from Tsinghua University in the automotive engineering in 2018. After that, he got his PhD degree in civil engineering and scientific computing from U Michigan, Ann Arbor in 2023. He's currently a postdoc there, working in the civil engineering department. His research interests lie in enhancing the safety performance of the connected and automated vehicles, including the naturalistic driving environment modeling and automated driving system evaluation. He has served as a member of the SAE Onboard Automated Driving Verification and Validation Task Force. He was the recipient of multiple awards, including the Exceptional Paper Award from the Transportation Research Board annual meeting, and also the Intelligent Transportation System Best Paper Award from the INFORMS Transportation Science and Logistics Society in 2021. So these are just some of the awards he has received. Obviously, he has done very exciting and very interesting work. So we are very happy to have this great opportunity for Xintao to share his exciting work. So Xintao, I will leave it to you.
Thank you so much. Thank you. So good morning, everyone. Today, I would like to discuss some research progress we had on safety assessment for autonomous vehicles. So autonomous vehicles technology has the great potential to significantly improve the transportation safety, efficiency, and also sustainability. Therefore, it has attracted great attention from both industry, academia, and also government agencies. And this interest really peaked at 2016. So at that time, multiple OEMs has announced that they will commence mass production of autonomous vehicles by 2020. So obviously, we're in 2024 now. There's currently no commercially available autonomous vehicle product. And you can see the reality falling short to meet the ambitious expectation made by that time. And in 2022, the Fortune magazine actually had an article said they could have a long and cold winter for the self-driving cars industry. In particular, last year, Cruise had a severe accident on the streets of San Francisco, and later on it suspended all driverless operations after this event. And fortunately, in just like a few months before, there's some news saying that Cruise has already resumed some of the tests recently. And also there's some more encouraging news in this year. So this British startup company Wave has already raised $1 billion this year and closed a new high for Europe-based AI funding deal. And also Waymo has announced that they will expand the autonomous ride-hailing service area in the Bay Area, including San Francisco, Los Angeles. So you can really see that the autonomous vehicle technology has experienced like a roller coaster wave during these years. And there are numerous reasons behind it. And we believe one of the main concerns for this autonomous vehicle is lying in its safety performance. And if we made a comparison between human drivers and autonomous vehicles, an average human driver will experience one accident for every 10 to the power 5th or 6 miles. So it's around 500,000 miles for one crash. And if you compare with autonomous vehicle, for the most state-of-the-art autonomous vehicle, it will have a one disengagement for every 10 to the power 4th miles, based on the disengagement report from the California DMV last year. So you can see there's at least one order of magnitude or 1 or 2 order of magnitude gap between the autonomous vehicles and human drivers. And this gap will really hinder the development and deployment of the autonomous vehicles and for public trust. So this is why we think safety assessment is really critical. For one perspective, you need to have some quantified measurements for the autonomous vehicle safety performance before we have mass deployment on the road. And doing safety assessment also can help the development, because during the test, you could identify those long tail and unknown issues, and this can be used for further refine the AV algorithm and make sure the development process is closed loop. And more importantly, if you have a transparent benchmark for those like autonomous vehicle safety performance, this could enhance the public trust and enhance the confidence. And this is also important for legislation agencies to establish like safety protocols for these AV companies before they have commercial products. So in these slides, I would like to explain what do we mean by safety assessment for autonomous vehicles. So this is basically a Monte Carlo estimation process. If you drive the autonomous vehicle in the naturalistic driving environment for n times and experience m times of event of interest, for example, collision, then you can have an estimated crash rate calculated by m divided by n. So here you can see that the key here is that we want to do this in simulation because the simulation is controllable, repeatable, scalable, and more importantly, cost-effective. And the key challenge for doing this is how you can develop a high-fidelity simulator that ensures that each realization of your simulation will follow this underlying distribution of real world. We denote it as PX here. This is an extremely complex and high-dimensional distribution because there are large amounts of human drivers and they have complex interactions for long time horizon. So this is the first challenge we could encounter the curse of dimensionality for modeling such a simulation environment. And even more, the event of interest A is a rare event in real world traffic. As we mentioned, human drivers will experience an accident for 500,000 miles, which means if you want to do this using a Monte Carlo estimation process, you will need a very large number of n to get an accurate testing results. As pointed by previous literatures, you need billions of testing miles to test an AV if it has the same safety performance as human drivers, which means even if you do this in simulation, this is very time consuming and sometimes even not practical and not acceptable. So to solve this problem, this basically is a real event estimation problem. Researchers have proposed a method called importance sampling. So the idea is that instead of sampling from your original distribution Px, you construct a new distribution called Qx. and this is called importance function. Intuitively, if you think that if you expose the AV to more safety critical events in this newly designed test environment, it could reduce the number of tests needed to reach an accurate estimation. And based on during the importance sampling theory, for each test, it will have a importance likelihood. Basically, it's a weight for each of the tests. And by applying these weights to each of the tests, you can still ensure your testing is unbiased, but with significantly less amount of tests needed. So the key challenge here is how you can develop such a new environment we call naturalistic and adversarial environment to accelerate the process. So we decompose the problem of safety assessment of autonomous vehicle into two problems. The first one is that how you can leverage large amounts of naturalistic driving data and reconstruct such a simulation environment. And it needs to, this part is important because it ensures the trustworthiness of your testing results and ensure your testing is unbiased. And the second step is how you can develop an NADE, naturalistic and adversarial driving environment based on this NDE to try to accelerate the process to achieve an accurate and efficient testing procedure for the autonomous vehicles. And in today's talk, I will cover both parts, and let's move into the first part. So first, I would like to introduce the current practice of simulating NDE that's being applied by industry and also academia. The most widely used approach is called log data replay. The idea is very simple. You collect a lot of data from real world and you identify those events that have safety critical events, and you replay the background agent's behavior based on this logged data, and you will control your autonomous vehicle with an updated version of algorithm to see whether its safety performance improved. So the deficiency of this type of method is obvious. This type of environment is non-reactive, which means the background agent, because it's replayed trajectories, it cannot interact with the autonomous vehicles, new version of your autonomous vehicles, so you cannot really test the effect of your improvements after your newer version of the software. And another widely used approach is to use some simulation environment like traffic simulator, for example, like the Kala or Sumo. And the basic idea of this type of simulator is that you divide the behavior of human drivers into car following models or lane changing models and gap acceptance model. And by heuristically decompose them into several different models, so you can propose different numerical models to simulate the human driver's behavior. However, usually these type of models are oversimplified. For example, the widely used car following model, IDM, intelligent driver model, it has 5 parameters you need to calibrate. However, you can hardly reproduce the complex human driving behaviors using only 5 parameters. So that's the reason why this type of simulator could be subject to heuristics and not realistic. And recently, there are also methods proposed based on deep learning and data-driven methods. And the overall pipeline is try to train your model to reproduce the observed trajectory by using some deep neural networks, and this is widely used for like the trajectory prediction. However, it should be noted that the pipeline for developing like the trajectory prediction methods is try to minimize the individual trajectory level accuracy, like the displacement, average displacement error, final displacement error, miss rate, for etc. However, this is not equivalent for your environment level accuracy. And also, trajectory prediction is an open loop process, which means your prediction will not be executed. And this is different from your simulation, which is a closed loop. So the distribution shift issue will be severe when we do the simulation. And this is a major challenge. So the first question we need to answer is that how we can measure the safe simulation fidelity for AV development purposes. And we argue that your simulated environment should be statistical realism, which should be statistically representative of real-world environment, especially for those safety critical driving conditions. And I will use an example to demonstrate why it's important. So consider a roundabout scenario. There are 2 vehicles. Vehicle 1 is circulating in the roundabout, and vehicle number 2 is at the entrance and about to merge. And let us assume the distance between these two vehicles in real world, they follow an underlying ground truth distribution as shown in this red curve. And if your simulation has a different curve, like the curve like as shown by this dashed blue curve, you can see it is statistically it's distributionally different. And you will find out they could have a different for the estimated crash rate. For example, if you assume the distance, if the distance smaller than a certain threshold, if you consider it as a collision, so there will be differences of the estimated crash rate. So if one of the vehicle is autonomous vehicle, which means your simulation will provide an optimistic estimate for the autonomous vehicle performance, and you will generate a biased results, and this could make your safety assessment results not accurate. And also, if you train your agents in such an environment, the agent trained might not be able to fit in real world traffic due to this large sim to real gap. So you can find out that unrealistic simulation might lead to mislead AV development. And so in our work, as we mentioned, the real naturalistic driving environment is characterized basically by the state of each of the agent during the whole time horizon. It will lies in a very high dimensional space. And our simulation is trying to imitate this distribution and sample from it to generate each realization during your test or training. And because this high dimensional distribution is so complex, you have no ground truth. So we cannot verify it. So what we did is we try to verify on some of the marginal distributions, some of the important marginal distribution, like the vehicle state distribution. For example, the vehicle velocity, the distance, the origin destination, traffic volume, and etc. All those like widely used matrices in transportation area, we need to verify them, ensure your simulation is consistent with the real world. But more importantly, there are new requirements bring in for this autonomous vehicle application is that you care about safety critical events. So the simulated safety critical statistics should be consistent. For example, the crash rate, the crash type, crash severity of your simulations should be consistent with the real world. And also, in addition to collision, we also care about near miss, because near miss is also an important event you need to test for autonomous vehicles. So the near miss statistics should also be consistent. So that's the whole philosophy behind our naturalistic driving environment modeling concept, is that we want to develop such a statistical realistic environment for simulation. So to tackle this problem, we develop a deep learning-based method called the neural NDE, and try to reproduce such a naturalistic driving environment with statistical realism. And it has been published in Nature Communications and featured as a journal front page article. And I will introduce in details. So we framed the behavior modeling under imitation learning paradigm with deep neural networks under the supervision of real-world data. So basically, you want to obtain the joint distribution of all your simulated agents based on their historical states and also environment context information. And we develop this as a unified model. So we do not need to introduce subjectivity of behavior states. Like we don't need to decompose the behavior into car falling and lane changing. So this can reduce the subjectivity and improve the fidelity. And we assume the joint distribution of multi-agents will follow a certain distribution. In this study, we assume it follows a multivariant Gaussian distribution. So basically, you need to generate the mu and the covariance matrix for the joint distribution so you can sample from it to generate the action. And to accurately model it, we use a transformer as a backbone to develop the whole model. And here is introduction for the network structure. So actually, it's very straightforward and simple. So the input will be the historical states of all agents in your environments and the historical and also traffic signal states in the environment. And we will use frequency encoding, input embedding to elevate them into a higher dimensional feature space. And then we'll stack several block of transformer layers and then use prediction heads to obtain the predicted distributions. And here we output the mean and variance for the Gaussian distributions. And here we use we follow a BERT structure. So we use an encoder only structure for the transformer backbone. And so we train it use some open source data. Here we use a roundy data set. This is Julian roundabouts located in Germany. And here I was first play a video. So here all vehicles are simulations. All vehicles are controlled by our algorithm. And so in these slides, I want to first take a look to see, so really the model can model the interaction between agents and see how they influence between each other. So we highlight one of the vehicle number 2. So consider this vehicle as your like your ego vehicle, and we will showcase different colors, showcase what is the influencing weights of all surrounding vehicles on this ego vehicle. And the brighter the color, the higher the influence. Okay. So let's look at 3 important representative moment. For example, moment 42. Oh, sorry, let me. Okay, somewhere here. Okay. So at this moment, you can see the vehicle, the attention weights of the vehicle number 2 puts the most of the attention weight to the vehicle number 44, which is the vehicle in front of it, which is intuitive, right? Because the vehicle is currently behind this vehicle and the car following it. So the model learns that it should place more attention to its leading vehicle at this moment. And if we look at the next moment, for example, moment 94. Okay, somewhere here. Okay, somewhere here. So at this moment, the ego vehicle is about to enter the roundabout. So firstly, it pays a large attention to vehicle number 45, which is the vehicle in the roundabout and currently has a potential conflict with the vehicle number 2. And more importantly, you can find out it also pays a large amount of attention to itself, to its own historical state. The reason is that if the vehicle has a high speed previously, then maybe the vehicle number 2 will not choose to stop but just aggressively merge in. But if the vehicle number 2, as shown in this example, currently have a low speed and already stopped, then maybe this vehicle will also choose to stop and yield to this vehicle, and after that, it will merge into the roundabout. So which means that its own historical states will also have a large influence on its behavior at this moment. So finally, let's maybe look into the moment 219. So it's at the end. So when the vehicle is about to leaving the roundabout, so you can see there's no vehicles around it, so it pays a large amount of attention to itself, so which is also intuitive. So from these results, you can really see, okay, seems like, okay, the problem solved. You have a model that can generate the simulation, seems reasonable. It has the attention, looks correct. So, okay, let's generate the simulation. So we run a large number of simulations, use these models, and we find the result is not good enough. So we find out the simulated crash rate is around 2 times 10 to the minus 1 crash per kilometer, but the ground truth for this location is around 1.2 to the time of -4, which is, you can see the simulated crash rate is significantly higher than the real world. And also your generated crash type is also not consistent with the ground truth data. So the reason is that the behavior modeling network cannot achieve distribution level accuracy in those safety critical conditions because your training data is overwhelmingly coming from normal driving conditions. So in those safety critical part is not well trained. So it makes your simulation not good enough. So that's why we further developed 2 modules called conflict critical module and safety mapping network to try to improve the modeling accuracy here. And I will use some figures to illustrate the idea. So the output of your behavior modeling network will be the joint action distribution of multi-agents. So there could have unrealistically high conflicting probability due to the modeling accuracy. So after you sample the behavior, there could have potential conflict. Then every time you will pass through your sample trajectory at every moment to this so-called conflict critical module. Basically, it will output a certain acceptance probability. You will have an acceptance probability PA that you accept the conflict to occur, but also you will have certain probability to reject it. And if you sample to reject this, you will pass through a safety mapping network to try to rectify the behavior of your previous sampling actions and try to resolve conflict. So the idea here is that if you carefully calibrate your conflict critical modules, make sure you acceptance probability, so you can basically control the generation process of your safety critical events and ensure it can fall in the real world occurring frequencies and patterns. So you can control the process and generate the safety critical events as like the real world. So here I will briefly introduce what's the safety mapping network. Here is basically neural networks that guide the vehicle behavior. And you can train to imitate a lot of model-based methods. Here we use a physics-based methods. The idea is that when the two vehicles are going to collide with each other or have a conflict, you will have like the repulsive force on both of the vehicle and try to push them away. It's like a deceleration of the green vehicle and acceleration of the blue vehicles. So basically, we try to use this module to rectify the behavior and resolve the conflict. And we can pre-train this neural network using a large amount of offline data. And here is the final, like the training pipeline for the neural NDE, is that we adapt a GALE framework, generative adversarial imitation learning. So we introduce a discriminator here, try to distinguish whether your simulated trajectory is realistic or not, to try to further tackle the distribution shift issue in simulation. And also, we not only sample for one step, like in the trajectory prediction method, we can roll out this trajectory roll out multiple times to ensure during the training process, you can imitate like what you are doing in simulation. So you can also further improve the model performance, try to tackle with the distribution shift or what we call error accumulation issue. So it can further improve the performance. Okay, so I want to first play a video. So one of the video is purely data replay of real world trajectories, and one video is pure simulation. It's simulated by our models. So you can see from both videos, there are realistic behaviors like the yielding, merging, communications between vehicles, and also even sometimes like the overtaking within this like two-lane roundabout, as shown in, let's wait a little bit. So you can basically see pretty looks good. Okay, like here, like the overtaking, like in the two-lane roundabouts. So arguably, it's visually indistinguishable. So the left-hand side is real world, the right-hand side is pure simulation. So arguably, it's like looks realistic in human sense, right? So this is like more like a qualitative analysis. And then we want to move into like do the real quantitative analysis. So, but using the open source data, you don't have like the crash type data in those data sets. So we choose a location in Ann Arbor, state of Michigan. And in our previous project of our group, we have developed some road perception system in this two-lane roundabout. This is a very busy and complex roundabout. It has the fourth highest crash rate in the whole state of Michigan. So that's why we choose this location. And we have installed this device here, so you can collect the data 24/7. So you have a large amount of data. And also we have the crash reports for last 10 years. So all this data can serve as a ground truth to validate your model performance. And here I want to first show a video, shows that our method can generate realistic collisions. So on the left-hand side is real-world collision events happen and captured by this roadside camera. So you can see this is angle collision due to the fail to yield of this vehicle, and the collision happens here. And in our simulation, we can generate very similar patterns, but pure simulation, you can generate this type of fail to yield situation. And the second example is about the size-wide collision caused by improper land usage. So you can see these two vehicles was driving in parallel previously. And later on, one of the vehicles just improperly steering into other vehicles' lane, and the collision happens. And we can also simulate such like similar patterns in our simulation. And the last one is the rear-end collision. So in this example, you can find the following vehicle failed to maintain a safe gap with its leading vehicle. So rear-end collision was happened here. And also we can generate similar pattern in our simulations. Okay, so after all this like qualitative analysis, what we really argue is statistical realism, right? So here's some results. So the simulation setting is like for each simulation we run for 1 hour. So it's really long time horizon simulation, and we run 15,000 15,000 simulation hours in total to collect the data. And we verified both the normal driving condition statistics and the safety critical condition statistics, including crash events, near-miss events, and also a lot of matrices we use in transportation, like speed distribution, distance distribution, yielding behavior, origin, destination, traffic volume, and etc. And due to the time limit, I will mostly focus on those like safety critical matrices. So the first one we care about is crash rate. So the crash rate of the simulation is 1.21, 10 to the power of -4. And the ground truth is 1.25, 10 to the power of -4. So you can find this is pretty similar. And also, so crash rate is a more overall measurement. We can also generate the detailed composition of different types of crash and also the severity of the crash based on the difference of crashing, the speed of the two agents at the crash moment. So we used 5 years of data happen at this specific roundabout as the ground truth to obtain the ground truth distribution. And we can find our simulation showing this orange bar is pretty similar to the blue bar as shown as the ground truth. So we can find we can generate realistic crash events in our simulations. So in addition to collision, we also care about near miss. So we use two measurements to measure the near miss. The first one is vehicle distance distribution. So we measure the distance between any of the two pair, the pair of vehicles. And if you consider like the distance smaller than 10 meters as a dangerous situation, the orange distribution shows the simulation and the blue bars shows the ground truth. You can find our simulation overall can generate a high accuracy simulated distance distribution, and also it can achieve good performance in these safety critical situations. And also we use the PET, the post-encroachment time, which is a widely used measurement for near-miss event. Basically, it's the time difference between two agents pass through a conflicting area. So the smaller the PET, the more dangerous the situation. So we rasterize the roundabout into a lot of small cells, and each cell you can consider as a potential conflict area. And your PET distribution of the simulation and the ground truth are shown here. You can see it still like looks good to achieve a consistent results. And here I only briefly want to showcase that this is a vehicle instantaneous distribution, distance distribution, yielding speed, yielding distance distribution generated by our method. And we compare with a sumo, with a calibrated sumo model. You can find our method can outperform the sumo model and generate a much more realistic distributions. Yeah, so that's the first part I want to cover in this talk is about how you can generate the simulation to ensure, because this is the foundation for the development and also the testing of the autonomous vehicle. So in the second part, I would like to introduce how we accelerate the process to make sure your testing is efficient. So the idea of the naturalistic and adversarial driving environment is developed from NDE, but with some of the sparse but adversarial adjustment of the behavior of the agents. So for most of the time, the agents will follow a naturalistic behavior in most of the situations. And only at specifically identified moment and identified agents will perform some carefully designed adversarial moves to try to challenge the autonomous vehicles. So you can enhance the probability that an autonomous vehicle encounter safety critical events, so you can accelerate the process. So the whole idea here is that we want to train the background agents to learn at what circumstances, like which background agents will perform what adversarial moves at how much probability. So that's the idea of the NADE. So this can be formulated as a reinforcement learning problem. So at the specific state S, we want to output the action. We want to basically refine the action distribution of each agents and try to improve the testing efficiency. And so the idea is that we can develop the reward function based on the importance sampling theory, because to optimize the estimation efficiency is equivalent that the importance function 2x to minimize the estimation variance. So we can develop a reward function based on this idea and we try to train this using the deep reinforcement learning paradigm. However, we find that it cannot be properly trained if you directly formulate as a DRL problem, still due to the curse of rarity issue, because your safety critical events is so rare in your NDE, which makes your reward is very sparse during the training. So it will introduce a large variance when you try to train this in such an unbalanced data set, and you cannot achieve good performance. So this is recently our group, Professor Liu has a paper called A Curse of Rarity for Autonomous Vehicles, discussing that the rarity of safety critical events has on the autonomous vehicle development. So to tackle this curse of rarity issue, our group developed a method called dense learning. So basically, we try to identify those. We try to basically densify the training data set and try to overcome the curse of rarity by using this method and make sure the training is possible. And this paper has been published in Nature and featured as the cover article for that issue, for this issue. And so I will introduce the idea of dense learning in these slides. So let's consider a general deep learning problem as an example. So it's basically training is like an optimization process. You essentially want to get the gradient estimate expectations to try to fine-tune your model parameters and to minimize your objective function. And for DRL, the key is to estimate your policy gradient to perform this gradient descent process. And your data in our application can be divided into two parts. The first one is those like safety critical events. We call set, maybe classify them as a set B. And also you will have those non-safety critical data, which is overwhelmingly dominate your training data set, and we call set A. And if we do not do any sampling and use all those data to obtain the policy gradient, you will find out that those non-informative data will dominate the process. And basically, they will contribute 0 for the expectation for the gradient, but with large variance marked as by these gray arrows, and make those informative data, the direction of the gradient, be buried under all those noisy information. And after, if you use all of them to get the gradient descent, you will have a very rare signal to ratio, noise ratio. And the idea here is that we want to use develop some method to identify only those safety critical events data and use them to get the gradient. And theoretically, in the next slide, I will discuss that we theoretically prove that the estimation, the gradient estimation, the expectation of the gradient is unbiased if you use all of data or using only those safety critical data, and but with a much smaller variance, so you can accelerate the process. So here is basically some statistical analysis of the results. Is that we prove that the expectation of both of the gradient expectations are the same, but with a much smaller variance. And the scale, like how much we can decrease for the variance, is proportional to the size of the data set A. So the large amount of proportion of the non-informative data, the better performance you can achieve for reducing the variance. And due to the time limit, I won't go into the details. So if you're interested, you can check in this paper for details. So in our application, basically we developed some of the safety matrices to separate the whole state space into 3 parts. The first one is crested, and also another part is called critical state, basically some of the near miss or safety critical situations, and also the other one is uncritical states. So normally, the training data will be like a Markovian decision process, and transverse during different parts of the state space, and you will get some of the reward and do the back propagation. So the idea here is that we will identify those critical states and shown by this pink cell, and we'll perform Markov process editing. Basically, we will only connect those critical states and omit those like non-critical states, and only back propagate the reward through these critical states to update their value. So by doing this, we can ensure the information identified and properly trained for these deep dense neural networks. So here is some results. So on the left-hand side, we showcase the crash rate estimation using the both NDE method and also the dense learning methods. You can find they converge into the same number. We showcase the testing in the NADE is unbiased, as in we test in the naturalistic driving environment. And the right-hand side figure shows the convergence curve. So the y-axis here denotes the relative path width. And when it's below 0.3, we will consider it's already converged. So we can find out if you test this in NDE, it takes 1.9 times 10 to the power of 8 number of tests to reach and converge results. But in NADE, you can achieve the same level of accuracy with only around 5 times 10 to the power of 4 number of tests. So you can see our NADE approach can achieve a 2,000 times faster of the testing efficiency, and we still with the unbiased estimation results. And this can reduce millions of testing miles, so you can significantly save your money during testing and also accelerate your development cycle. And also, we also showcase some of the results for the crash rate and crash severity, and it also make sure your testing is unbiased, not only for crash rate, but also for crash type and severity. And with the NDE and NADE, we basically build comprehensive testing tools for autonomous vehicles. And we already try to deploy in real world to test some real world autonomous vehicles. So here we use Mcity's real autonomous vehicle, the OpenCAV platform. So it has it's a retrofitted Lincoln MKZ with a variety of sensors installed. And the software stack, we are using AutoWare. So it's an open source autonomous vehicle software stack. And we use it as the autonomous vehicle under test to serve as our test benchmark. And in order to do this in real world facility, we developed the augmented reality testing platform. Because in real world, there is no background vehicles. You cannot put like hundreds of vehicles in the testing facility to test it. It's too dangerous and very costly. So we developed this AI platform. The idea is here is that on the left-hand side shows the simulation view. We can synchronize all those information and send it to the autonomous vehicles through like the DSRC or V2X communications or through internet. So from the autonomous vehicles perspective, as shown in this view, this is RV's view from the AutoWare. From its perspective, there are a lot of surrounding agents, and it needs to properly interact with them. And the right-hand side is doing the real-world implementation. So here's from camera view doing the test, and we can superimpose all those like AR, the background traffic using those images, and superimpose them into this from camera and use to generate this augmented camera view. And we can use this platform to test autonomous vehicles. And we deploy this platform in 2 testing facilities. The first one obviously is Mcity in University of Michigan. And second one is ACM, is American Center for Mobility. It's a commercial testing facility. And here is a video showcase the testing process. So here is real Lincoln MKZ running Mcity. And we can find at each moment with the D2RL, we'll try to identify what situations, like which background vehicles are important and like what is adversarial maneuver. For example, here is a cut-in and whether you should sample it. For example, the probability here is only 2. So we actually did not sample it at this moment. And then we continue running in this time continuous traffic environments to test the autonomous vehicles in like a 24/7 manner. And for example, here is a roundabout situation. So at this moment, the principal of the vehicle will try to aggressively accelerate. to evaluate whether the AD can properly react, and the collision happens at this moment. So basically, we generate we find out a crash angle collision at this moment, and we have based on this likelihood, we can obtain the estimated crash rate and obtain the relative pathways, and also generate the crash type estimation and crash severity estimation. And the idea here is that you will do this, run a large number of tests following the same process, and conducting after doing the running process, you can obtain the estimation of your crash rate and all other statistics. And after you converge, you will stop, and you will get you can think you are already finished the testing and get the final results. So this is real world implementations. And so here's some references about the work I covered in these talks, and please check it out if you are interested. And I would like to note that all the codes I mentioned in this talk are already open source. So you can try the code, run the experiments, and if you have any questions, feel free to reach out. And finally, I would like to acknowledge for my advisor, Professor Henry Liu, for leading the whole research program and our team. And also, I would like to acknowledge my collaborators and our research sponsors. And that's all. And I would like to honor to be here, and I'm happy to take if you have any questions.
Yes, excellent. Very interesting introduction. I'm going to give this opportunity to other folks here to see whether we have any questions here. I have some, but I'm going to save them in the end. Hi, Menchi. So how are we going to handle the questions? Do they just unmute, or did they input them in the text box?
Yeah, I think Mansi would be the moderator, but
Yeah.
until she comes online. So I have a general question for you. So how will this approach, which is very interesting, I think all the work that you've done, it's very nice and deep. But I was wondering how it would deal with, crazy behavior by humans, like maybe like road rage or adversarial sorts of conduct by humans.
Yeah, so thank you, Professor. So the question is basically how we can ensure your naturalistic driving, your testing environment covers diverse behavior in the real world. So I think the answer is that is still rooted in our belief for the statistical realism. So we believe in the real world traffic environment, their human drivers' behavior have some underlying hidden distribution. And like the road rage or this behavior is equivalent to like the vehicles will have like aggressive cut-in or aggressive merge, all those behaviors. So our idea is that as long as you have all of this data and you so we would like our environment to be able to cover the whole distribution of the environment. So that's why we would like to verify whether there are like situations that with very small distance between vehicles, and also like with those yielding behavior in that roundabout. For example, in that roundabout case study, we identify, we examine the yielding joint distribution between the yielding distance and the yielding speed, like at what circumstances the vehicle will yield. And we compare this with the real world data. So as long as your data contains such rare or crazy behavior, and you can basically verify whether it's already being reproduced in your simulation. If not, which that means your simulation is not good enough, and you need to further improve it to make sure it covers all those range of behaviors. And then your next step, you can accelerate it to generate more frequently for those behavior to test it. So that's the overall idea.
Okay, yeah, thank you.
Are there any more questions?
Maybe I will ask one as others prepare to get the questions. So I'm curious, Xingtao, so let's say if I'm interested in testing the situation to see whether it can replicate the situation in Raleigh. So you did that for another, right? That roundabout. So if I'm interested to learn that in Raleigh, so how feasible and how difficult is it to transfer all this framework to another place?
Yeah, thank you, Professor Chen. That's actually a very challenging and good question. It's about the scalability and the generalizability, basically, for the whole system to testing diverse different locations or road geometries or environments, basically. So in our current framework, our model, like basically you need the data for your testing locations, and you need those data to be able to train your NDE, NADE, and you verify it to make sure it's statistical realism and then test it. However, if you want to directly transfer, for example, you have another data and we train a model, currently could be challenging if we want to directly transfer to a new environment because the driving behavior could be significantly different and the testing result could be biased if you're directly using those data. So what we are trying to do, or a feasible solution is that you train a model with a large amount of data from diverse locations using like the open source data set, for example, the Waymo open data set. And basically you have a general behavior model, general simulation models for covering diverse geometries, locations, and situations. And then for your interested location, you have a very limited or small amount of data, and you try to fine tune your model to make sure this model can specialize in your interested locations. And you use this fine-tuned model and cross-reference with some of the historical data. For example, crash reports, using some crash reports from the city to see whether the crash type or all those statistics fits your local situations. And after doing that, you can have some confidence saying that your environment is good enough to represent your environment. And I think this pre-training, fine-tuning pipeline could be a feasible solution.
I see. Yeah, that makes sense. Just one thought on that. Let's say if I want to transfer to another place for Raleigh's case, do you have any sense of like how much data we really need? Because in my imagination, let's say if you get the data for a month, it probably already has a good representation of the typical traffic, particularly the near miss cases. But it may, and of course, it may not include those like real crashes because those are really rare. So, yeah, I guess maybe it will be helpful to treat these separately. And then if you're not able, or let's say if you're only able to have a small period, let's say a month or half year, then maybe is able to already provide a good coverage of near miss cases. And then only gather the crash data because those will be much closer, right, for multiple years. So maybe the resolution is very low. But maybe only some of the episodes in those really crash events are needed to get this actual crash. No, just wild thoughts.
Yeah, actually, I agree. I think 1 month of data for like your interested location is already enough. So in our case study, for example, for that another roundabouts, we find out actually if you only want to model like the normal or behaviors good, you only need like 5 to 8 hours of data for that specific location. That's enough. You don't even need several weeks. I think several days of data will be sufficient because we are currently using like an infrastructure-based data. So in each of the frame, you cover a lot of vehicles, and all of these their behaviors contribute to learn the model. So so that's the reason I think that's different from like the vehicle-centric data, like the Waymo data sets or like Algoverse data sets. They are vehicle-centric. You have, yeah, that's the difference. So that's the reason. And also because we have those like the conflict critic module, you can trick with. So you, even if you don't have like the real crash trajectories, and but you have some crash statistics like the crash type or crash severity, you can still use the framework and make sure these overall statistics are fit. But if you are lucky enough to have some crash trajectories, of course you can maybe do more to further edit, to further cross-reference whether like the acceleration, deceleration before the crash happens are fit or not. But that goes into another level of fidelity. That's like more even trajectory level or frame by frame examination for the realisticity. Yeah. But in general, I think several hours of data is already enough for one location. I mean, for specific location. Yeah.
I see. Yeah, that's very helpful. Yeah, I think we have some questions in the chat box. I'm going to leave it to Mcity.
Mcity, I think you muted.
Yeah, I'm muted. Yeah, I was saying there are a couple of questions in the chat box. I see one by Abhinav Sharma. You could answer that.
Yeah. The question is how you had balance between the normal events and safety critical events in the training data set. Okay, so the question is how we avoid the autonomous vehicle where we have an over conservative or aggressive depending on the number of scenarios or environments. So again, so here what we did, I covered in this talk is mainly about testing rather than like the development, training of the autonomous vehicles. So we are trying to evaluate its performance. So in both of the two parts, NDE and NADE, we try to ensure we are unbiased. So in NDE, basically, we ensure your generated crash events are fit with the proportion as the real world situations. So that's why the crash rate is important. And this is exactly why we argue that crash rate is pretty important, because in most of the existing simulators, the crash rate could be significantly higher than real world. And this could like generate a issue, as you mentioned. If you train your model in such simulation environment, the vehicle could be overly conservative because it's encounters so many crashes in the simulator. It has to be cautious. So that's for NDE. And for NADE, in NADE, we enhance the frequency of generating all these events. But for each test, we will have an importance like the likelihood. Basically, is to map each event back to the original frequency in the real world. So that's to ensure that your testing result is unbiased. So that's why we use that experiment to demonstrate that your test estimated crash rate is the same for no matter you're testing NDE or NADE. So that's another way we try to avoid the environment being biased to mislead the development of autonomous vehicles. Yeah, I hope that answered the question.
Yeah, thank you. I think since we've run out of time, we may not be able to take any further questions from the chat box, but if anyone has a question, they can speak up. Any last questions that they have?
I think there is another one in the chat box that asking, I think it's a vision from Sintel, like how the AVs will play out in the future years. Oh, yes.
Yeah, that's also a very good question. Actually, from my perspective, so in recent years, there's a roller coaster wave, but I'm pretty positive to this technology. And I think really in recent like 1 or 2 years have some advancements in this area. For example, like the development of this generative AI, this like from OpenAI, from the Google or Tesla, it's really have major milestone moving forward for the deep learning or those like the artificial intelligence technologies. So I really think they are beneficial for the autonomous vehicles. And also from Tesla, like in this year, they have released a lot of versions. And I did not try it, but I watched a lot of videos online. So it looks like it's really pretty intelligent in lots of cases. It can even understand the human gestures in some of the situations during the driving. So that's pretty impressive. And yeah, I think the autonomous vehicles, this is like the normal curve of emerging technology, right? You have a very like the hype at the beginning and then going down and then maybe starting moving up again. So I think we are on this part now. It's like at the tipping point for really transfer the momentum from like going down from several like last 2 years and then moving up. So I'm positive to this technology. Yeah.
Yeah. Thank you. Yeah, we've run out of time now, so unfortunately we won't be able to take any more questions.
Yeah, and people can
Maybe
contact.
Xingtao, you can share your email here. So if the students or any other people have questions, maybe they can reach out to you.
Yeah, sure.
Thank you, everyone.
Thank you.
Thank you for the great talk, Dr. Yan.
Thank you so
Yeah,
much.
thank you very much, Xingtao. So we
Thank
have
you.
learned a lot. Yeah, I think we will check more.
Thank you for
Thank you
having
very
me.
much for today's wonderful talk.
Bye.
Thank you. Bye.
Thank you.